We've had several requests to make a video that explains the cable rating factors and cable choices to be made as shown in Appendix 4 of the Wiring Regulations book. So, in this video from LearnElectrics, we'll take a look at this and show you a method to use the tables that are found here that will help you in your work life and in exams and assessments. Many have asked what the symbols mean and how to use the rating factors shown in Appendix 4. Others have asked what the equations mean, the ones with all the letter C's. Where do you even start with it? For this video, we will assume that we are selecting twin and earth cable, as this is a popular cable in domestic work. If you can understand how to manipulate the equations for twin and earth, other cables will be easy too. Tables and data will come from the 18th edition Amendment 2 Wiring Regulations book, the Brown Book. This is the only book allowed in the 18th edition exam, and if you are studying for this exam, then I do urge you to follow the steps in this video and learn how to access pages quickly. When working on site and for certain electrical assessments, there is some limited information in the on-site guide on page 167 and the few pages that follow, but not as much and as informative as in the big Brown Book. Let's begin with part 2 of the Wiring Regulations book, and all the tables shown and page numbers relate to the 18th edition Amendment 2 book, and definitions begins on page 46. There is a list of the C rating factors at the top left of the page, and a short description of what each symbol means. To the right of each description, there is also a reference to where you can find examples of that symbol, that rating factor, in use in the book. We will concentrate just on circuits above ground, as described in Appendix 4, Section 5.1.1 on page 425. The blue box and arrow are pointing to the basic equation, and this is the one that frequently comes up in exams and the one that we will use in this video. Because we are only concentrating on circuits above ground, some of those rating factors, the C rating factors, are not applicable to us as shown here. And for modern consumer units, we do not need the CF rating factor that is used for the old BS 3036 fuses, although there are still many thousands of them out there, and we will do an example of this in the video. BS 3036 fuses are the semi-enclosed rewirable fuses from the 1950s, and the blowing of the fuse wire, the melting of the fuse, is not as instantaneous as the more modern breakers. To compensate for this, we apply a fusing factor just for 3036 fuses. You will find information relating to this and the fusing factor on page 424 of the Regs book. CI is the rating factor for thermal insulation, loft insulation being just one example. The table on page 423 is a popular choice for exam questions, and exam setters love tables. Notice that this table is only for cables totally surrounded by insulation. Reference method 103 for twin and earth cable, as we shall see shortly. This is table 4A2 on page 437. It shows the 4 installation reference methods that we apply to twin and earth cable where the cable is in proximity of insulation. These are methods 100, 101, 102 and 103, and we shall see how these are used very soon. Remember how to find this page. Again, it's a popular choice for exam questions. While we are here at Appendix 4, let's show you why we often quote 70 degrees Celsius as a limiting temperature for twin and earth cable. It's because we are told to. Take a look at the table on page 440. This comes from BS 6004, the standard for different electrical cables, the law on cables if you like. As highlighted, we can see that this table directs us to use 70 degrees Celsius as the limiting temperature for flat profile twin and earth cable as listed in table 4D5 on page 456. CA is the rating factor for ambient air temperature, and these factors are detailed in table 4B1 on page 441. And this is an easy table to use. Choose the ambient air temperature in question, then find the corresponding entry for 70 degree thermoplastic cable in the case of twin and earth, and then read off the rating factor. This is another exam question table. Be sure to know where it is in the book. Two things to note. 30 degrees is the reference temperature when the rating is given a number, a value of 1. In other words, a rating factor of 1 makes no difference to the cable rating. And secondly, an ambient temperature of 25 degrees has a rating of greater than 1. It makes the cable size, or CSA, smaller. And this is the only time that this happens. All other rating factors will make the cable size choice bigger. CG is for grouping, for cables grouped or bunched together by different methods. Table 4C1 on page 443 shows the choices that we have. We can choose the installation method, and we can choose the number of circuits or cables bunched together. Again, a popular choice for exams. Now we come to table 4D5 on page 456. And I cannot stress enough how important it is that you can find this table quickly in any exam. It's used a lot for exam questions. Just looking at rating factors, once we have an answer from the equation, we will make reference to this table. We can find the reference methods along the top, the 100 numbers, and reference method C, etc. Looking down the chosen column, we will find a current carrying capacity that is at least equal to, often greater than, the answer from the equation. Once we have that, the table shows us the size or CSA of the cable that we must select. The table only shows the CSA for the live conductors, as this data is for use in a no-fault scenario when we are only interested in the line and neutral sizes. The earth or CPC will be whatever that size cable is made to. The on-site guide can be used as a reminder of how to apply rating factors. The information is there in Appendix F, but you cannot use the on-site guide in the 18th edition exam. Take a look, but we will use only the Big Brown Amendment 2 book for calculations in the rest of the video. There are three important I numbers that we must get in the right order. The first thing to establish is what IB is. What is the design current for the circuit? What maximum current has the circuit been built for? It could be a kitchen lighting circuit at no more than 4 amps, an immersion heater circuit at 13 amps, a ring circuit, unknown amps but protected by a 32 amp breaker. The design current is IB, or think of IB as I built. The design current, then, is what load the circuit is designed or built for. Next is IN. What is the nominal overcurrent rating of the protective device? Nominal, the name given to a breaker or fuse, for example. What is a breaker or fuse designated as? What do we call it? A 13 amp fuse is named a 13 amp fuse. 13 amps is the nominal rating. A 20 amp circuit breaker, 20 amps is the nominal rating. The name or number that is printed on the device. Nominal overcurrent device rating is IN, or think of IN as the I number printed on the device. In no-fault conditions, the nominal rating of the protected device must be greater than or equal to the design current. So IN the rating of the protective device must be equal to or greater than the IB, the design current. Think of it this way. You would not plug a 13 amp kettle into a 6 amp lighting circuit. The protective device, the fuse or breaker, needs to be at least 13 amps. Then we have IT. The tabulated current carrying capacity of the cable is IT. It comes from the tables in the wiring regulations book. Or think of IT as I table from the tables. If we go to the tables and find the required tabulated current carrying capacity of the cable, we can look at another table to find the minimum size cable required for that current with those conditions. If the cable is exposed to certain conditions, such as ambient temperature or groups of cables are bunched together, the cable may begin to overheat and might exceed the specified maximum temperature for that type of cable, 70 degrees Celsius in the case of twin and earth. It may be damaged by the increased temperature, and the cable insulation may no longer give the protection from shock that is required. And increasing temperatures can also affect the ZS of a circuit in a bad way. This is how the equation works. The cable rating, what the cable will take under normal conditions, as in table 4D5, must be greater than or equal to the nominal rating of the overcurrent device, and then divided by the conditions that the cable is exposed to. This is the standard equation, trimmed down for cables installed above ground. This will normally make the CSA or cable size bigger, as explained earlier. The important thing to note is that the cable will still carry the same design current. That will not change, but the conditions on the cable mean that a bigger cable size is needed to cope with the heat generated in the cable because of those conditions. This is sometimes difficult to grasp, so let me explain with the help of a cartoon. You might ask why the cable size changes for the same load. What difference does that make? Let's suppose that we have a 25 kilogram bag of potatoes just bought from the farm shop. We need to get the potatoes to the car. What luck! Here comes a Boy Scout. So we ask the Boy Scout to carry a 25 kilogram sack of potatoes across the car park to the car. He gets it done, slowly perhaps, but it gets done. Now ask the same Boy Scout to carry the same heavy 25 kilograms up a long steep hill in the blazing sun, and he will quickly begin to overheat and drop the potatoes. How do we solve the problem of the overheated Boy Scout? How about if we now ask a soldier, 10 times stronger than the Boy Scout? He will carry the same load up the same hill. He trains day in, day out to carry heavy loads, to run up hills in the sun with all his kit on. Easy. A 25 kilogram sack of potatoes is not going to be a problem. Now look at what we've done. It's the exact same 25 kilograms, the same load. All that we have done is to get a bigger and stronger person to carry them for us. The same happens with the electrical current. The load, the current is the same. We've just used bigger cables to cope with the overheating problems. We can do a couple of examples to demonstrate this. They are easy, and once learnt, the method will stay with you forever. The question asks, what size live conductors would you choose from table 4D5 when installing a twin and earth cable in a conservatory with an ambient temperature of 40 degrees Celsius? The circuit has overload protection from a 20 amp BS-EN 60898 circuit breaker, and we should assume installation reference method C throughout. No other ratings are to be applied in this question. We will calculate IT using the equation shown here, and the question tells us that IN is 20 amps. We can find the rating factor for CA by looking at table 4B1 on page 441. Because CA is the only factor of interest, we can now remove CG, CI and CF from the equation, and this leaves us with the very simple equation shown here. This is how I would calculate the answer. 20 amps on the top. Then find CA from table 4B1 on page 441. Find 40 degree ambient temperature for a 70 degree thermoplastic cable. This is a factor of 0.87. 20 divided by 0.87 is 23 amps when rounded up. This is IT, the tabulated value of the current carrying capacity for the cable, 23 amps. Now we can go to table 4D5 on page 456 and select a suitable cable size. IT, the current that the cable can carry without overheating, has to be 23 amps or greater. We are told in the question to use reference method C, so find this column. Work down the column until you arrive at a value of 23 amps or more, and this is 27 amps. Now move to the left to find the live cable size in the leftmost column. This shows that we should select 2.5 square millimeter twin and earth cable, and that's how easy it is to do. Let's do a second example, and this time we will have two rating factors to consider. Now the question asks, what size live conductors would you choose from table 4D5 when installing a twin and earth cable in an old bakery with an ambient temperature of 40 degrees Celsius? The circuit has overload protection from a 20 amp BS3036 semi-enclosed fuse, and we should assume installation reference method C throughout. CG and CI ratings do not apply. Again, calculate IT after finding the rating factors for CA and CF. This time we can remove the CG and CI ratings from the equation to leave us with a much simpler version shown below. Having found CA and CF in the book, we can put these into the equation and make the calculation. Our answer, IT, is a cable carrying capacity of at least 31.7 amps for reference method C. Now find a suitable cable size in table 4D5 on page 456. Using table 4D5, we should choose 4 square millimeter twin and earth cable. Notice that the more conditions that apply, the bigger the cable size may need to be. Virtually everything that we do to a cable will make the conditions worse, and as professionals we are expected to manage these correctly. There is an exception to the standard formula. The standard formula, the normal equation, uses IN on the top, but this different equation uses IB on the top for a very good reason. What if the breaker or fuse rating is not used, perhaps when overload protection is not required? Take a look at page 426. The equation for IT now has IB divided by the relevant C rating factors. As way of an example, if IN is not taken into account, how should we proceed? Imagine that a 13 amp space heater is hardwired into a 20 amp circuit breaker. The normal current will never exceed 13 amps. The circuit is used for nothing else. Can we choose a cable size based on 13 amps and not 20 amps? And installation method 101 will be used. Will there be a difference in cable sizes by using 13 amps and one using 20 amps? Using IB equals 13 amps, the IB rating of the heater, we can use the following conditions for the twin and earth cable. 40 degrees Celsius ambient air temperature makes CA equal to 0.87. Installation reference method 101, where the cable is covered by more than 100 mm of insulation. It's a very simple calculation. 13 amps divided by 0.87 is 15 amps. Consulting table 4D5 on page 456 and looking down the reference method 101 column, we see that we must select a cable with a current capacity of 17 amps. Moving to the left, we are advised to choose 2.5 square millimeter twin and earth cable. Now, exactly the same conditions, but this time using the 20 amp breaker for IN. The calculation tells us to choose a cable that will take at least 23 amps with reference method 101. This is 27 amps, and we should choose 6 mm twin and earth cable. That's a big difference. A very quick recap on what we've done. This is the standard formula for most domestic work where the cables are above ground. In the 18th edition exam, only the wiring regulations book is permitted, so learn to use this book and become familiar with the tables in Appendix 4. Practice now will give big benefits in the exam. Make practice questions for yourself to make your exam easier and to increase your competence on site. Apart from ambient temperatures below 30 degrees Celsius, the rating factors may make IT, the tabulated cable size, bigger, a larger CSA in almost every case. The actual load on the circuit, the real load, does not increase. It will stay the same. It is just the current carrying capacity that changes, the ability of the cable to cope with the different conditions, which is why we may need to select a cable that is rated for larger currents to compensate for those different conditions. Thank you for watching. It really is appreciated, and I hope that you found this video useful and informative. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at LearnElectrics.com. And don't forget, you can also type in LearnElectrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.